Alright. So starting today, what we'll do is we'll start discussing how to model simple mechanical systems. Okay. When I say model, see, last class we discussed the engineering process. Or let's say we discussed how to model the dynamics of a system, right?
We talked about force transform.
Right. So we discussed about the real world problem and applying physics and then translating, expressing that physics in mathematics, right? And then seeking a solution and then interpreting that solution in terms of in the real world. Okay. So today what we'll do is, now for the course, what we'll do is, this chapter is, or this section is frequency domain modeling.
One more time, Dr. Sun, you said how to model what?
How to model the dynamics of a system. It could be a mechanical system, it could be an electrical system, it could be an aerospace system, right?
Thank you.
When I say frequency domain modeling, this is modeling dynamics. Okay. Now let's start with simple mechanical systems. Okay. Simple mechanical systems would be consider a spring mass damper system. Let's think about okay. So look at this spring mass damper system. You have a spring. K is the spring constant. M is the mass constant. And C is the damping coefficient, which is again a constant. For this particular course, automatic flight controls, this is the sine. Okay? We limit our discussion to something called LTI systems. What are LTI systems? L is linear. And EI is time invariant. Okay. So what do you understand by linear time invariant system? What is a linear system? What do you understand by linear system?
It constantly changes with time.
Y equals mx plus d.
I'm just thinking the slope of the line.
Alex, what is a linear system?
Was it linear system?
You hear linear systems all the time. What do you understand by linear systems?
The change is constant.
Huh?
The change is constant. That's
What is constant?
The
What
slope,
change?
the slope is constant. The slope is constant.
Slope of what?
The slope of the line.
What line?
The line, which is the
The
equation.
the
The
line.
equation. The line equation. Wow.
The
Or
only
the
line
function.
there, like in a given amount of time,
The
No,
function.
it's
You're right, but you have to define what that line is.
The line is
So,
the
for
line
example, if
solutions.
you're considering y is equal to mx plus c, right? The line, that is the line, correct? Now, what is, you have to think about x as an input and y as an output. The input-output relationship, that line is the input-output relationship, right? So, you have, if you draw that y is equal to mx plus c, you have your x on the x-axis, and then you have y on the y-axis, right? So when you, whatever values you take for x, the y value is changing only linearly. So this relationship, so all this are, these all are linear systems. Input-output relationship is linear. Got it?
input out.
So that input-output relationship is very important. And what is a time-invariant system? When we are talking about time-invariant system, now think about here. Time invariance here means the k is not going to change with respect to time. What does that mean? So if you consider the spring as time progresses, does this k change? The spring constant, does it change?
No.
It's a property of what? The spring constant, k. It's a property of the material, it's the property of how quickly you wind it, how you compress it, all that, right? So that is not going to change as time progresses. Again, mass. Is mass a time varying quantity?
No.
Not in this case.
In our case, we don't deal with time as a varying, mass as a time varying quantity. You understand? So what that means is, in aerospace systems, although in aerospace systems, mass is a time varying quantity. Why?
Because fuel.
Because of the fuel, right? If you think about the rocket as a system, rocket is a time varying system, right? Launch vehicle is a time varying, it has a time varying mass. So if you're trying to apply control systems theory to controlling a rocket, you cannot apply that directly to the rocket. You have to linearize. You have to piecewise linearize. So if you have, what is a non-linear system? So if you have x and this is y, this could be a typical non-linear system. Right? So what you do is, you break this up and you make it piecewise linear. You understand?
son, you said that would be a typical what?
This is a non-linear system.
Oh.
So you can break this up into small portions and linearize. You get it? So then that is how you will apply your this control systems theory to a non-linear system, to a neurospace system. You break it up for whatever portion this is, whatever portions it is linear, you break it up and apply it to control systems. Okay? Again, C is the damping coefficient, it's a time invariant quantity. We consider that as a time invariant quantity. Okay? So you have to remember this whole course deals with linear time invariant systems. We only learn linear control theory. This is also called linear control theory. You apply only linear systems. Okay?
You said linear control theory?
Yeah. Now you have this. So what you're seeing here is you have to pay attention to how I use this notation. Okay? So as I told you, this K, M, C are time invariant quantities. Now how about f of t? F of t is force, and x of t is displacement. Okay? So this is force, this is input, and this is displacement is output. So you will see that input output are time variable, right? Otherwise it doesn't make sense. Then you are not really studying dynamics. Okay? So this force is changing with respect to time. So that's the reason it is written as f of t. And x of t is again displacement. So if you apply force here, right, you see that as an input, there will be a displacement. Correct? You agree?
Yes.
Now how do you model this system? What physics are you going to use? Yes.
When you say I think I'm confused by terminology. When you say time invariant, that's not saying with respect to time, is it? What do we mean when we say
This quantity is time invariant. This quantity is time invariant.
and what does that mean?
It doesn't vary with time.
Oh,
Got it?
yes.
Okay. So this should make sense. The applied force could be changing with respect to time. If the applied force is changing, the displacement will also change. Okay. Now, how do you model this? How do you model the input-output relationship? You apply Newton's second law. Okay. So you think about this. I can simply write this as f of t or mx Okay. So this is based on Newton's laws. Now if you want to understand this, I'm going to explain this only once. Okay. You have to make sure you model it accordingly. So this can be written as mx double dot plus c x dot plus k x t is equal to f of t. Okay. So you think about, recall f is equal to we'll just use the simple simple notation of Newton's second law. F is equal to ma. Alright? For this purpose, we also assume that the mass of the spring and the mass of the damper is negligible. Okay? So here you can say masses of spring and damper are negligible. Alright. So when you apply this force here, what happens to the spring?
It's pulled.
Hmm?
It's pulled.
It's pulled, right? So it is actually, there's a force due to the spring acting in the opposite direction. Right? So if you pull a spring, what happens? The spring is trying to apply force in the opposite direction. Right? So you have F of P. And what is that force equivalent to? That force is equivalent to K, spring constant, into the amount of displacement. Right? Again, when you apply that force to this dampener, this damper is also going to try and go back. Have you tried to, you know what a damper is?
Hydraulics.
Hydraulics. So when you push it or pull it, it's going to try and go in the opposite direction. Okay? And that force is equivalent to the velocity, the damping coefficient, into the velocity of your displacement, or the velocity with which you apply. So it is x dot of t. And that is equal to mass into acceleration. Right? What is the mass? Capital M.
Can you explain the damping one again?
So damping, think about a dashpot or a hydraulic. You know what a dashpot is, right? Think about a dashpot.
A dash box?
Dashpot.
I don't know what that is.
Dashpot.
I don't know about that.
That's fine. Think about a hydraulic system. Okay? So if you think about a hydraulic system, if you try to push it, it will try to push you out. The velocity if you try to push a hydraulic system very fast, it won't go in. Push it slowly. Have you tried it? It will go in. If you try to push it hard, the force will be much more. Okay. So the force acting due to the damping is proportional to the velocity with which you push it. Okay. So this force is acting in the opposite direction. This is just a force component, nothing but a force component.
That's the mass times acceleration.
Huh? This is mass times acceleration. This is acceleration. Right?
What's the
This is the applied force, this is the induced force, and this is also the induced force because of how the system is built.
equation?
So this equation is the same as this equation. You see?
Yeah.
You just moved everything to the other side.
Yeah, this and this are the same. So I just moved f of t there and moved this cx dot and kx.
Which is the way it's supposed to be because it's going in the opposite direction anyway.
Right.
Those-
So this is the exact application of Newton's laws. Okay, the force is going in the opposite direction. If you apply force this way, the induced force is going in the opposite direction. Okay, all that will cause this an acceleration in the mass. Right. So that's what you know according to Newton's laws. Now, what you need to do is this is your system modeling. Do you see this as a differential equation? Is this a differential equation? Huh?
It can be because it's a bunch of functions.
It's not can be, it is a differential equation. Don't you see this? There's a derivative here. What's a differential equation? Your prerequisite 307.
Yeah.
What did you learn? Quincy, is this a differential equation?
Yes.
You see, it's obvious. It's a differential equation. You see a double derivative, it is a single derivative, right? this is what I was discussing in the last class. You take a physical system, right? And now, see, this is the input-output relationship. So what is the input here? Again?
Input is the
Then-
force.
yeah.
For
F of t. And what is the output?
The output is the displacement.
Right. So if you look at this, what will you solve for when you're look at this as a differential equation? What will you try to solve for?
X.
You will try to solve for x, right? You will seek a solution for x. Okay. So that is given a force, given an applied force, you want to know at a given instance of time what is that x, what is that displacement. You could also be interested in finding velocity, right? Then you will solve for x dot of t. Depending on what you are interested in. These are all states, position, velocity, acceleration. Depending on what you are interested in, so this is a known quantity. Force is a known quantity, right? The applied force. You should know that, what kind of force you are applying. Okay? So this is how you model a system. Now, apply Laplace transform. Okay, so this L, I'll just use this. I'll use this part, this thing. Okay, this will be the usual form which we'll use a lot. We have mx double dot of t plus c x dot of t k x of t is equal to. Okay. So this is equal to. This is simply equal to m s square x of s plus c s x of s plus k x of s is equal to f of s. See, if you compare this one and this one, nothing has changed. Okay? Here x of s is what? It's just the displacement expressed as a function of
Frequency.
frequency. What is f of s?
Function of frequency. Well, force after so many
Force.
over time.
Force expressed as a function of
Frequency.
that's it.
So okay, so that second line, we have the s squared for the second derivative,
Mm-hmm.
right?
Mm-hmm.
But then we have another x,
X of s.
x of s.
X of s means this means displacement expressed as a function of s.
Right.
It
right.
doesn't have any meaning.
Where
See
was this?
again, this one doesn't have any meaning.
Okay, so where was the equivalence to that x of s in the previous line?
Where? This x, do you see x double dot of t?
Yes.
So it turns out to be, this m remains as it is because it's a constant.
Right.
The Laplace of x double dot of t
Uh-huh.
is s square into x of s. Yes.
The second term, is that x of s squared?
That
This
little black line you got.
Just again, erase that.
So it is x of x. So here it is single derivative, right? So you have s into x of s. Plus you don't have any derivative here. So this function of displacement as a function of time becomes displacement as a function of frequency. Right? You have to pay attention, okay?
When you say
Alex,
Yes, sir.
please pay attention. So
when you
here x of t is a function of time, displacement is a function of time. Here k remains as it is because it's a constant. The Laplace of, so here let me show you. So this, you can write this as, you could have written this as something like this. Laplace, so you have m into Laplace of x double dot of t, okay, plus C Laplace of x dot of p plus k Laplace of x of p is equal to Laplace of f of p. Okay, so this comes out to be m into Laplace of x double dot of p is a square into x of x plus c. This is s into x of x. K into
Earlier when you said that, I think it was the x of s in the second line. When you said it had no meaning, what did you mean by that? You said it.
What it means is, see this f of s, for example, let's take as f of s. Okay. When you write something as a function of time, it just means that we don't know what kind of force it is. What is the pattern of the force? You just know that it's a time varying quantity, right? So if for example it could be an impact force, it could be a slowly applying step force. Got it?
Right. Okay.
So whenever somebody writes like this, it means it's just a function of time, but we don't know the exact form. Got it? So here we don't know it. We have expressed this displacement as a function of time. But this will depend. This will depend on what? This will depend exactly on this. Depending on what kind of force you apply, what is the pattern of the force, this will change. Okay. Now what we can do is we can write this as, think about this. X of s is equal to, sorry. So you can say ms square plus cs plus k is equal to. Okay. Now you have to notice one more thing here. This is calculus, right? Do you see any calculus here?
No.
It's not transformed to
Algebra.
algebra. This is just a polynomial in x. So this is the other, that's what I was trying to tell you last class. Calculus has its own domain of solutions. Similarly, algebra has its own domain of solutions. So if you convert that to calculus, you have a whole domain of solutions which you can solve. Now if you solve for this x of t, x of s, and take the inverse, what are you going to get? You're going to get x of t. Got it? So that's what we are trying to do here. You solve for this x of s, right? And then you take the inverse of that. That will be x of t. Inverse Laplace of that. Okay?
So you have to do this in order to get x of t and can you solve?
We could have solved for x of t here. What would you have done? You would have done a homogeneous solution and a particular solution to this, right? You would have equated this equal to 0 and then found a homogeneous solution. And then you would have gone for a particular solution. And then you would have solved for x of t.
So you'd rather choose the concept?
Yes, so what we are doing is we are converting that from a time-based model to a frequency-based model. We are also changing the calculus to algebra and seeking solution in algebra and then taking the inverse to get a solution for this. The solution will be exactly the same. If you seek a solution, differential solution, calculus-based solution, and you seek an algebra-based solution, you compare those, that will be exactly the same.
So this was just straightforward Laplace, but to find that x of t that Michael was talking about, we would basically go backwards, which would be the inverse.
Right. So if you take, for example, if if somebody is, will also learn this, we can just directly model the system as a frequency domain model. Looking at this, right? You can model that system as a frequency domain. You don't even have to do this. You'll actually do that. So if you do that, you'll straight away get this. Okay? You straight away get this. Then if you take the inverse, what are you going to get? You're going to get this. Okay? So this is your simple spring mass damper system. Now here you have to consider what is the order of the system. What is the order of the system?
It's the second one, sir.
It is the second order. Why is it the second order?
Because it's the second derivative.
Right. It's the double derivative, right? Second order system. Now we are going to deal with, we may be introduced to 1 mass, 2 mass. If it's a 2 mass, it will become a 4th order system. Okay?
A 2 mass will become a 4 what?
4th order system. Okay. This mass is what makes it a second order system. Is Laplace transform, is applicable, is the utility of Laplace transform clear?
Yes.
Clearer, at least clearer than last time?
Yes.
Yes, the Laplace part.
You guys are done with. Okay.
The mass you just said makes it a second order, but then you said if you have 2 masses, it will be a 4th order.
Right.
So each mass is 2 orders.
Right. What do we need to do for today?
Spring mass.
If you have, so we'll. You could be doing something like this. So if I give you something like this, it shouldn't be too overwhelming. We have to deal with 2 displacements, x1 of t. Okay, this is f of t. Next class, the reason we there is something very interesting about the spring mass damper. Okay, you can practically model any mechanical system. And everything we know, everything that is physically, that is tangible, physically tangible, is a mechanical system. Right? Even aerospace systems, the structure is a mechanical system. Any mechanical system can be realized using the simple spring mass damper. You understand what I mean? Does it make sense?
Can you say that one more time? Even a what can be?
For example, you could build your entire aircraft, the physical part of the aircraft, using a spring mass damper. Or at least you can realize using it just a spring mass damper. So what are wings? What are ailerons?
Ailerons, like,
Can you realize using the spring mass damper system?
I can see where that's hydraulics come into play.
Yeah. Hydraulics will come into play, springs will come into play, right? So that is the reason we study spring mass damper system. Now if you have something like this is a 2 spring damper system. Now how do you go about modeling this?
That's going to be 4th order.
4th order system. So what you do is you consider mass 1 Using model mass 1 and then you do the modeling same for mass 2. Okay. So we'll stop here. I just want to we'll discuss this next time. Please pass on the attendance sheet. While we do that, when do you? It will be 2 equations, but it will be 2 second order equations. That will be a 4th order equation, right? Now, when do you want your lab? I know you sent an email and Quincy sent an email saying you guys cannot make it on Thursday. What time is convenient? Because Tuesday, at the exact same time, I have another lab. I don't know why it was scheduled that way.
Can that lab move to Thursday?
No, I've tried. That is a much bigger class. I tried doing that.
So wait,
Monday.
so we have lab tomorrow.
Huh?
We have lab tomorrow.
We cannot have lab.
Wednesday, we got, well, yeah,
Oh.
Tuesday at 5. Start at 5.
We can have Wednesday.
I got 4 to 6. ROTC.
You don't have to do it in the afternoon. You can do it in the mornings as well.
That's what I was gonna say.
Can you do it, let's say,
We got mornings on Tuesday.
Do it.
Because we already.
We start class at 8:30.
We got Arizona.
Tuesdays?
Yeah.
9:30 to 10:30.
So Thursdays
And
at
then he has
11.
a class at 11 on Tuesday.
I'm saying we can do the lab on Tuesday. After that,
But that's only 30 minutes because he has 11.
oh, you have 11 to 12, right?
The Tuesdays book that.
hmm?
The Tuesdays are booked that.
Yeah, it's Tuesday.
Tuesdays,
What about Wednesday, 1 to 4?
I have class.
Mondays, how about Mondays?
Monday?
Mondays.
Oh, yeah, Mondays are good.
Mondays, what time?
We can do it, he's saying it's not gonna be early. What time your class?
Oh, we can go before school.
4 to 5, so we can do the lab from
Is it
11 to 2.
literally going to be 3 hours?
Is it
one,
It's not,
like 2 hours?
we'll have to schedule it, but it need not be 2 hours. It
Okay.
need not be 3 hours.
But at least we need to make sure we do.
One.
2 hours.
we can do 1 to 4.
Z got
That's
that
what
time.
I
11, what
On
about
Monday?
11?
The only time on Monday can be 11 to 2. Is it? It got
How about 11 to 2? I think 11 to 2 will work.
We got.
We have class. We have
Class
class
at
from
11.
12. So what if we did 12 to 2?
Thursday.
He got-
How about Thursdays? Thursdays, you're not free at all during the morning?
The morning.
How about, huh? Thursday mornings should be fine, maybe 9 to 12,
I have class at
11.
11. And you have class at 11 too.
Yeah, you got it.
What if we had
Let's do this. So Thursdays, how about 8 to 11? We'll schedule it, we'll just schedule it between 8 to 11.
Time.
Huh?
But what
Why
about
not?
Thursday afternoon? Nobody can do Thursday afternoon. What time RTC start? 2?
I can tell.
Thursdays, anytime is fine. Thursdays,
Well,
not
yes.
just not 11 to 12. So 12 to 3, how about 12 to 3?
No.
Why not?
Yes.
Yeah.
From 1 to
It might have to
2:30.
be late.
1 to?
1 to 2:30. I have class on Tuesday to Thursday.
It might have to be late.
Fridays?
Friday, what time? What if it was Friday? Oh, but you have class.
How about 12 to 3 Friday?
We can, because she got class.
1 to 2?
Wait, 1 to 2. So what about 2?
2 to 5?
2 to 4 on Mondays.
He has a
That
class.
goes into
Yeah,
Saturday.
2 to 4 on Wednesday.
What if we do 2 hours one day
2 to 4 on
and 1
Wednesday.
hour another day?
I can do
Wait,
2.
what?
2 to 4 Wednesdays.
But
2
you
to
said
4 Wednesday.
Yeah.
2 to 4
Well,
Wednesday, 4
You
Wednesday.
got 4 o'clock. Yeah, I have 4.
Well, you gonna leave at 4? No.
2 to 4 Wednesdays. 2 to 4 Wednesdays.
We have to schedule it for 3 hours.
2 to 4 Wednesdays?
No, we have to schedule it for 3 hours.
Oh.
2 to 5.
2 to 5 Wednesdays.
Yeah, I just start.
Huh?
group, so we can always just,
It's not gonna take the whole 3 hours.
You gonna be there guaranteed 2 hours.
yeah, and probably a little over, but you know,
2 to 4. I'm here for it. Or 2 to 5.
2 to 5.
2 to 5.
Friday 2 to 5.
Right?
2 to 5. 2 to 5. No, 2 to 5 Wednesday really will work.
But you have a class from 1 to 2, or you have a class from 1 to 2?
Doesn't
5
affect
is
time.
good.
2 to 5 is perfect.
Everybody's happy with 2 to 5. Wednesday. That works.
Okay. But he's excused, okay? You guys are not excused.
Oh,
We'll be there.
Alex, you're not excused, especially.
He's
gonna go. Alright,
Alright,
so seriously, I want you to Alright.
You have something, Austin? Okay, only Austin and
And John Lewis are excused. And y'all, whatever group you're in, will just fit into that last portion. Because we usually get out. Like, yeah. So.
We need to love
You may not get out,
Not every
so
time.
everybody's not every time. Yeah, that's
Yeah.
And then we have
But-
to work 5 to 7, so we can't stay past 5.
that's fine.
Yes.
Yeah.
Well, y'all was enough time.
Wednesday.
Alright, so we good?
Yeah.
Alright.
It's from 8 to 7.
So we got get into this design work class.
So 2 to 5 on Wednesdays? John Lewis? That's okay?